The Hurwitz zeta function, denoted by zeta S, A, is a generalization of the Riemann zeta function, which plays a central role in number theory and related fields. The Hurwitz zeta function was introduced by the German mathematician Adolf Hurwitz in the late 19th century, and it has since found applications in a wide range of mathematical contexts. The Hurwitz zeta function is defined for complex numbers s and a with the real part of s greater than 1, and a not equal to 0, -1, -2. By the infinite series, zeta s, a sigma n0 nas, where the sum is taken over all non-negative integers n. This series converges absolutely for s with real part greater than 1. And it defines the Hurwitz zeta function in this region of the complex plane. Like the Riemann zeta function, the Hurwitz zeta function can be analytically continued to other values of s, with the exception of a simple pole at s1. This analytic continuation is a fundamental aspect of the function, and is essential for its applications in number theory and other areas of mathematics. The Hurwitz zeta function satisfies a number of important properties and identities, many of which generalize properties of the Riemann zeta function. For example, it satisfies a functional equation that relates its values at Sn 1s, and it satisfies certain reflection and translation formulas that express its values at S and S1 in terms of each other. The Hurwitz zeta function also encodes deep arithmetic information. For example, its special values at positive integers are related to Bernoulli numbers and Bernoulli polynomials, which are fundamental objects in number theory. These connections are reflected in various formulas and identities involving the Hurwitz zeta function and Bernoulli numbers or polynomials. The Hurwitz zeta function appears in many areas of mathematics, including the theory of modular forms, the study of special functions, and the theory of L functions. In the theory of modular forms, for instance, the Hurwitz zeta function appears in the Eichler integral representation of modular forms, which is a key tool in the study of these objects. In the theory of special functions, the Hurwitz zeta function is closely related to the gamma function, the beta function, and various hypergeometric functions, and it provides a unifying framework for studying these functions. In the theory of L functions, the Hurwitz zeta function appears in the functional equation of L functions, which is a central result in the field. The Hurwitz zeta function also has applications in physics. For example, in the context of quantum field theory, the Hurwitz zeta function appears in the computation of certain Feynman diagrams, which are graphical representations of interactions between particles. In the context of string theory, the Hurwitz zeta function appears in the computation of certain string amplitudes, which are quantities that measure the probabilities of various string processes.